The appearance of Paul Dirac in this series may seem a bit of a surprise, since the series promotes the practical side of physics, using pictures, etc., while Dirac is a self-declared admirer of mathematics and its beauties. But possibly because of this, he wasn't satisfied with the Schrödinger equation, despite his successes, as being not relativistically invariant. And that indeed is a problem. For example, do the same with the double slit experiment as one does with light clocks, etc. in relativity theory. Look at it while standing still or from a moving train. When using the standard form of de Broglie's wavelength relation, with momentum in the denominator, you get the familiar upper illustration when standing still. But when in a train moving towards the right together with the electron, seeing these as stationary, you get a lower one, with a much smaller wavelength, because now it's the much more massive equipment that seems to be moving. Or abbreviated, you get different results in different frames of reference. Here it is in terms of the quantum mechanical formalism. That is, the two formalisms, the standard and the de Broglie one, are on the left, and their experimental predictions for the moving observer on the right. There's no choice. The standard formalism, the one on top, is incorrect. So Dirac was justified in his assessment. And therefore, what he started with was not the non-relativistic Schrödinger equation, the one that worked for atoms, but the relativistic one that did not. Now one can note that the one working is linear in the time derivative, while in the one not working it is quadratic. So one usually says that Dirac also made the relativistic one linear. That may seem so, but in fact what he did is to put the non-linearity somewhere else. And just as with de Broglie, in an afterwards surprisingly simple way, he factorized the equation, and because of the is zero at the end of it, you can then take either of the two terms. One usually calls it, you take the square root of the equation. The Dirac equation is all about this process of factorization. This factorizing is easy for quadratics of the form a squared minus b squared, as shown, but gets more difficult for a squared plus b squared. That could be handled with complex numbers, but then you still have no solution for the expressions with more terms, as in our target equation. Here's the approach taken by Dirac. Assume that you already have succeeded, and now determine what relations your factorizers alpha and beta have to obey, which in its first step is high school arithmetic. Here's the result. So the problem is now, how can you get especially the second of these two expressions to work without getting zeros? The answer is well known once formulated this way, by turning them into matrices, because the second expression is the anti-commutator of alpha and beta, and since this is zero, the commutator is not zero. And simple mathematical forms that do not commutate, as regular numbers always do, are matrices. And if you make the matrices as simple as possible, 2 by 2 and using ones and zeros, you'll quickly find solutions like the ones shown. So what you have done now is like taking the square root of a squared plus b squared. And if you give this sum a finite value, you've taken the square root of a circle. But how about a squared plus b squared plus c squared, which is what you need as soon as all spatial directions are involved? The answer to that one was already available at the time, the Pauli spin matrices. And indeed, Dirac did use them as building blocks for his solution. So the solution for the three-dimensional case can be written down as shown immediately. And what you have done now is taking the square root of a sphere. But the relativistic energy relation adds the square of rest energy to the three squares of momentum, so the procedure of adding dimensions must be repeated one more time. Here's a set that does the trick, where the I is the identity matrix. But there are many others of these sets, for example differing in the places of the minus signs. In the following, some of these other sets will also be used. And what you have done now with the help of these 4 alphas is taking the square root of a hypersphere. Now a hypersphere cannot be reproduced even such that it gives merely a poor impression, but to show a hypercube is somewhat more doable. And of that, the rather unimaginable hypersphere, one takes the square root. And with these 4 alpha matrices, one can finally factorize the relativistic Schrödinger equation, with the one shown as one of the factors, which is then the desired equation linear in the time derivative, the Dirac equation. But as noted, there are many other matrices that satisfy the factorization rules, so there are many representations of the Dirac equation. The usual one involves the slightly different gamma matrices, and with them you can get the well-known and aesthetically pleasing relativistic form of the equation as shown. However, here we want things to be more practical, and this is what you get after writing out the sigma and the spin matrices. It shows first of all that the Dirac equation is still a direct offspring of the Broglie oscillation. Just remove the space dependence. In fact, if you resolve it for a single component, you get back the relativistic Schrödinger equation. The difference is that the single component of the Broglie oscillation now has become 4. Whereby one can also see that the Dirac equation isn't linear at all, it just has its quadratic nature hidden in there being multiple components that are coupled to each other. What these additional components mean physically becomes clear if you take the mass to be 0 in the equation with the sigmas, which results in the one shown, which is called the Y equation. This consists of 2 uncoupled equations, each with 2 components connected by the spin matrices, whose solutions propagate with the speed of light, and whose spins are opposite. So its solutions look like this. They are usually associated with neutrinos, even now one assumes that the neutrino masses are not 0. Coming in pairs of opposite orientation, one is the neutrino and the other the anti-neutrino, particle and antiparticle, which is a natural product of the process of factorization. The eigenvalues of the factorization matrices have opposite signs. One of the things taken from this for the solution of the quantum problems is the fact that the sigma matrices will of course also appear in the solutions of the massive Dirac equation. And another thing taken with it is that in describing a particle with spin as a half, the solutions will obey the Pauli exclusion principle. Being a principle is probably the reason that only one illustration could be found, coming from colleague part G. However, as an old-fashioned physicist trying to use simple and practical physics, our philosophy is that nature doesn't follow any principle, nor does it obey any equation. Nature does things, and that doing things lead people to formulate principles, etc. So it's not the differential equations that represent physical reality most closely, it is their solutions, the wave functions, which do that. Applied to the exclusion principle, this means that it must have a physical representation in the wave functions. Here taken to be that they cannot occupy the same space, of which the illustration seems to give an intuitive explanation. This concept is an essential one for the model of quantum mechanical interaction to be developed in the next part. The previous illustration then immediately suggests an intuitive explanation of what does go together with this illustration. And lo and behold, that indeed is something that one can find in real-life physics in the process of annihilation of particle with its antiparticle. And, almost superfluous, the existence of the Dirac equation definitely confirms that the Schrödinger equation is not the fundamental equation of quantum mechanics, and that the wave-particle relation is not a duality, because the Dirac equation is the fundamental equation of quantum mechanics, and contains rest mass, so its solutions are present permanently. In fact, one didn't need to go this deep in the derivation of the Dirac equation to come to this conclusion, due to the knowledge of the existence of spin. here shown in the form of the Zeeman effect, the splitting of spectral lines in the magnetic field due to differences in spin. Spin can only be included into the Schrödinger equation by putting it into the equation manually, which was done by Pauli, but from this could have been seen that the Schrödinger equation is not fundamental. However, with the spin included, the Schrödinger equation leads to the correct solutions for the atomic state. So how come? That is, of course, because the Schrödinger equation can be derived from the Dirac equation, which is a standard procedure. Here by rewriting the earlier given version of the Dirac equation, the one with the sigmas, giving the first expression shown. The second expression is the way the Schrödinger equation was derived from the single component relativistic one in the previous episode. The similarity can be seen immediately. Finally, at this point, having wave functions with the properties of spin and the exclusion process, we now have enough information to build on quantum mechanics from the quantum formalism, which is started in the next episode.